Hello, everyone, and welcome back to 4-H Computers. This is our Project 1 recap. As you recall, last week we learned about transistors, which are like an electric drawbridge that allows one wire to disconnect another wire, like that Tinker Toy diagram I made before. And I claim this is the greatest invention of the 20th century. And here is the first little experiment that we can do with that and what we were asked to do last week. Now, as you can see, if you just look at the top of this diagram here, okay, we've got the output of the circuit here, which is marked as this bar means not. So not A and B is what this means. So this output is supposed to represent, it's supposed to be true whenever it's not true that A and B are on. Okay, so if either A or B are off, then this should be on. But if both A and B are on, then this should be off. So if you just look at this part of the circuit and you ignore this down here, just this top, you can see that we've got positive voltage here, pull down resistor here, which means a resistor that's just connecting you to a default value, right, which is the high voltage. And then it just goes over here and you see that the circuit is on, right? So by default, not AB is on, right? And that's the state it should be in unless both these buttons are pushed over here. Now down here, we see ground. Okay, that's 0 voltage. Okay, so if somehow we were to connect this ground all the way up through here, directly through here with no resistors, that would overpower the high voltage coming down from here through the resistor, right? Just like our analogy with temperature, if this were a chunk of wood. So how does it do that? Well, you'll notice here, this button, so it's not drawn, but imagine this button is also connected to a high voltage like this voltage here, and similarly this button. So when you push these buttons, a certain amount of current is going to pass through this resistor here, and it's going to turn on this drawbridge here, which is going to connect these circuits here, right? But unless this one's also pushed, it's just going to connect it to nothing because this circuit will still effectively be broken, right? Because this is a transistor, which means it's disconnected effectively. Whoops. Unless we get a positive signal to the base. The base is the middle here that activates the transistor, the drawbridge. You'll remember from our diagram, from our breadboard example project from last time that these little semicircular devices had 3 legs, and the one in the middle was the control. So you'll see if I push A and I hold down B, then both these are going to turn to high voltage, which is going to connect this circuit here and here. And then this low voltage will overwhelm the high voltage and our circuit will go low again. So this is how we make a NAND gate out of 2 transistors, okay? And you'll find out why we want to make a NAND gate later. But for the point of this experiment, we just wanted to show that we could make a Boolean expression gate using transistors. Now, in terms of what were challenges from last week, what can go wrong? Well, first of all, you need resistors for the transistor bases too. Last week, we talked about the need for pull-down resistors for our light, for our switches, and for our lights, something that would give them a default value if the circuit was disconnected. Circuit could be disconnected because you didn't push a button, or a circuit could be disconnected because your transistor was off, right? But in either case, you would want a voltage level that was pushing gently on the output to provide sort of a default value when the rest of the circuit was disconnected. So you do need those, but as this diagram shows here, and which I didn't mention last week, these transistors that we're using also want to have a resistor here leading into the base. Okay, it's just the way they work. I don't want to spend too much time on it, but that's the way they work. And that's why we had some trouble with one of our results last time. Another issue is resistor strength. Now we used some tiny resistors in our last project, but really we want 220 ohms for the lights and basically 10K for everything else. That's just the way these things are set up. 10K is the right default for switches, for transistors, and so on. But I want to emphasize, don't panic. This class is not about resistors. Okay, it's just about how our computer is possible, right? We're going to be de-emphasizing resistors more and more with each passing week. You're not going to have to spend much time worrying about, oh, is this the right amount of resistor, the right strength of resistor? So don't worry about that. And now I want to show you what I've done with one of the projects from last week. So I'm going to stop sharing and I'm going to bring this up here real close and I hope you can see it. This was taken from one of our students last time. And the only thing I've done is I've added a couple extra resistors here. Well, I've also changed the values of the resistors to 10K for most of them, but I want to see that it's still a familiar circuit we're used to. There is a button here. There is a button here. There is a transistor here. And there is a transistor here. And I'm going to turn it on. And we're going to see that immediately, hey, the circuit goes on. How about that? Sorry, I said the transistors were in the wrong place. There's a transistor here, and there's a transistor. There's that guy. You can't hide from me. Right here. Here's the other transistor right here. Okay. Now I push one of these buttons here. Yeah, nothing happens. Push this button here. Nothing happens. Note this light is still glowing full strength, right? Push both these buttons. Boom, there it goes. Perfect. Boom, boom, bang. Okay, you can see that we've got a nice little resistor here flowing into one of the transistors and another resistor over here flowing into the other transistor. And that was the problem we had last week. Nothing to write home about. But in case you're interested in getting this working, that's how we do it. And next we'll be on to project number 2. So I'm going to stop the recording now, if I can only figure out how.